Hello, I'm Andrew Lombardi, and this is my MECH 3380 semester project on a scissor lift platform and the optimization of the platform. Introduction. So for my senior design customer, I need to create a platform section that can raise from 30 centimeters to 72 centimeters, and it must be able to hold a person's weight of up to 300 pounds. This platform section will be used as a larger research tool. The platform sections will be placed end to end to create a walking surface for a person for use in research. The support points of the platform at its highest level have caused some concern that there may be excessive bending in the platform surface under load. So to investigate this, I've created a abacus model of just the platform surface. The platform surface is 60 centimeters by 30 centimeters with a flange that goes all the way around. Even though the platform was created to metric specifications, the analysis is done in standard because we are creating the pieces with imperial systems. So the material must be 6061 T6 aluminum with a modulus of elasticity of about 10,000 KSI and a Poisson's ratio of 0.33. The placement of the feet on the surface of the platform is shown here in the top image, and the points of support from the scissoring mechanism at its highest point of lift are shown here in the bottom image. So the design variables for this effort are the thickness of the surface plate and the height of the flange. The thickness of the surface plate can range from 0.125 to 0.5, and H can range from 0.5 to 2 inches. We've also like to maintain an aspect ratio of the height to the thickness of about 4 to 1. So why don't we just design for minimum deflection? Well, there are cost constraints on this project, and aluminum is very expensive. Some deflection of this surface is permissible, and what we've decided is that a deflection of around 0.01 inches is acceptable. And if we don't have to use the maximum amount of material, then that will save us money. However, this analysis could yield many results. When the thickness of the platform is low and the flange height is high, that could yield our design criteria. Alternatively, when the thickness of the platform is high and the flange height is low, that also could result in our design criteria. However, we prefer if the thickness of the plate is low and the height of the flange is high, since this would result in overall less material. So to set this up, we've created this model that shows how the weight is distributed evenly between the 2 feet. However, the pressure in these regions is not even because of the circle cutout. But 150 pounds distributed over this area and this area are both active. The support points on the underside of the platform are encastered, as shown in the bottom image. So with the initial design, our plate thickness was 0.25 inches and our flange height was 1 inch. This yielded a maximum displacement of 0.02399 inches. I believe we can do better. So we iterated the thickness and increased the thickness to 0.0275 and kept the height of the flange at 1, and this resulted in a maximum displacement of 0.02244 inches. Then iterated only the flange height with the thickness at original 0.25 and the height of the flange at 0.11 inches, and this resulted in a maximum displacement of 0.0198 inches. Using this data, we've created a Fourier approximation where you can see the design variables here with their deltas and the resulting deflections from those deltas in the lower table. It's resulted in a Fourier model shown here. In MATLAB, we've taken this model and we placed it in the optimizer function from in MATLAB. As you can see, we have the Fourier function here, and the design criteria is here. We would like the maximum displacement to be around 0.01 inches and maintain this aspect ratio. However, instead of placing both of them into the inequality constraints, because that would design for minimum deflection, I placed the deflection constraint in the equality matrix and the aspect ratio constraint in the inequality matrix. So what did this yield? The optimized design shows to be a plate thickness of 0.2393 inches and a flange height of 1.3497 inches. This resulted in Abacus in a maximum displacement of 0.01348 inches. So we did miss our target deflection by a fair amount. So why did we miss this target amount? Our optimized displacement showed a 27.46% error from our actual displacement. However, we also believe that the optimized displacement is still acceptable. First of all, it's still under what we had originally designed, and we believe that the error is acceptable, and the difference in the target versus the actual is also acceptable. We do not believe this will cause an adverse effect on the performance of this platform. We believe that the error is likely due to the complex nature between the design variables and that the displacement of the platform end is not approximated well by a linear model as is what we achieved with the Fourier. So in conclusion, we are happy with these results and we shall be moving forward with them. Thank you very much.